So we're going to start off chapter 11 here by looking at reactions of alcohols. So in chapter 10, we've seen reactions to make alcohols. Now we're going to show reactions on what we can do with them. So before we've been seeing reactions where we can start from a carbonyl and get to an alcohol, but now we can go the other way. Right now we can do an oxidation, because the other way, right, is called a reduction. And kind of remembering some of our Gen Chem terminology here, right? Leo the lion goes grr. We have oxidations when we're losing electrons and reductions when we're gaining electrons. So in this case here, right, going from this alcohol to this carbonyl here, right, we're losing electrons, right? We're losing two hydrogens. Or more succinctly, we're increasing the oxygen content or decreasing the hydrogen content, right? We're decreasing the hydrogen content, right? We're getting an oxidation. Okay, that's kind of the gist of it. So we're going to be looking at some oxidations here, going from alcohols, secondary or primary, to different carbonyls. So a big slew of these reactions are these reactions called organometallic reactions, meaning, right, we have metals and we have organic compounds as well. And a lot of these, as we can see here, take place using this metal called chromium, right, specifically chromium 6+. Right, we're not going to talk about inorganic chemistry very much, kind of it's beyond the scope of the class, but a lot of these reactions utilize chromium in some way. And there's two kind of big differences here between what we're using. Is this first one here, where you see the sodium or potassium chromium compounds, we can take secondary alcohols and make them ketones, or primary alcohols and make them carboxylic acids. So if we were to, for example, take a primary alcohol here and react it with this chromium compound with H2SO4 and water, and we're not worrying about the mechanism here, right? These mechanisms for inorganics are a little bit complicated and beyond what we're learning, but we can take this and go from, right, a primary alcohol to a carboxylic acid, just like this, right? That carbon is still there, but now, right, we have these oxygens on it, right? We've increased the oxygen content, we've decreased hydrogens, we have an oxidation occurring. And if we were to change this a little bit and instead, like, right, let's make this a secondary alcohol, we would instead have a ketone, just like this. And for these other compounds, right, this first one here, right, is a strong oxidizer. These other ones down below are weaker oxidizing reagents. 2 and 3 are, as you can kind of see, virtually the same, right? They're, quote unquote, weaker. I wouldn't say they're milder, these are kind of hazardous reagents, but they are weaker. So if we were to take, for example, I'm going to change this back to the original here with a primary alcohol. If we were to take the same primary alcohol and react it with these weaker conditions, PCC, which we'll see a lot, that's what this is, right? PCC, these oxidizing conditions. We can just abbreviate it like that, totally fine. We can do this PCC oxidation, and instead of getting carboxylic acid, we would get an aldehyde. Okay, and if we wanted to, right, we have this condition down here, which is kind of a caveat. We can add one of these reagents here to go further from the aldehyde, right? KMNO4, which we've seen a few times now, to add in an alcohol there, or to make it a carboxylic acid, right? So these are some different oxidizing conditions. So next we're going to look at some organic oxidation conditions. So without metals, right? And in particular, this reaction is sort of a we'll call it pseudo SN2. Right, there's sort of a partial SN2 reaction happening. And so we'll take a look at that now. So this reaction uses sodium hypochlorite, bleach, right, NaOCl, to do this reaction, okay? And the major product for this is a ketone, right? The secondary alcohol transforms into a ketone. And this is as far as we can go, right? You've probably noticed we're not looking at tertiary alcohols because we can't do oxidations on them because that'll lose a carbon, which we can't really do. So secondary carbons are kind of the furthest we can go. Okay, and this thing over here, tempo, which we use with primary alcohols, is essentially a quote-unquote stabilizing radical. Where you can see that radical electron in the oxygen. It essentially just allows us to use bleach more safely, right? Because as we all know, bleach is a pretty hazardous material to use. So what is the mechanism for this? We haven't looked at a lot of mechanisms, so let's get back into that. This one is a touch complicated, more so than just like an SN2 reaction, but we can still kind of observe what's going on here. So let's do that. So we have a lot of acid-base reactions occurring, and this first one here that happens is we have bleach reacting with acetic acid here down below, which is sort of our solvent and also something that's reacting in the reaction. So we have bleach coming in, right, and that sodium counter-ion isn't there anymore, right, it's just kind of hanging out in solution, and we generate this sort of quote-unquote quenched bleach here, bleach with that hydrogen on it. And what actually happens now is this reacts with another portion of acetic acid. So we can have this reaction repeating where that acetic acid, another equivalent of it, comes through, and we end up over-protonating bleach. Like this. And so now this is where this sort of SN2 reaction is taking place, where we actually now have our alcohol, our secondary alcohol here. It'll actually do this funky mechanism where it'll come in and actually attack the chlorine, right? Because we have H2O plus, which we can make into water, which is a great leaving group. So we can have reactions where we're actually also attacking the halogen itself and not have it as a leaving group. And so when we do this reaction, using a straight arrow here because we're no longer doing acid-base reactions, we get the following protonated alcohol and we do a final deprotonation here. And so we have this chlorine attached to the oxygen here. And so there's this final oxidation step that we're doing where it's another sort of SN2 reaction taking place where we can have another equivalent of base. We can use this deprotonated acetic acid that we have hanging around, and this will come in, grab that hydrogen, push those electrons up. Right now, that's what's making the double bond between the oxygen and that carbon, and chlorine leaves. And this generates our ketone. Okay, kind of a long, weird mechanism, but hopefully, right, this all makes sense based on what we know, right, doing these SN2-like reactions. So another reaction we can do is called the Swern oxidation, and Swern is just the name of the person/group that came up with this reaction. We're using these conditions here. We have oxalochloride, which is just this. We have DMSO, right, which we've seen before, particularly in these SN2 reactions. We have ET3N, which is just 3 ethyl groups on a nitrogen. This is our base, and we have an inert solvent. And so this, again, is another example of organic reoxidation, so metals involved here, but we get the same sort of thing happening. We have primary or secondary alcohols converting to aldehydes or ketones. So here where we have a primary alcohol, so we're generating an aldehyde, right? There's this hydrogen here. We won't worry about the mechanism. It's pretty complicated. I urge you to Google sworn oxidation mechanism and take a look at it. There's a lot going on here, so it's a little bit beyond the scope of what we want to sort of cover. But, right, kind of the key thing I want to highlight as we're looking at all these, right, is we're seeing a lot of the same sort of oxidations, right? We're going from either a primary alcohol to an aldehyde, or a carboxylic acid, or a secondary alcohol to a ketone, where we haven't really done anything different. We're using different conditions, but nothing's changing, right? And kind of the crux of the matter there, right, is that in reality, we're looking at the whole molecule, right? Or we're considering the whole molecule when we're doing these reactions. Meaning, right, in a lab setting, if one reaction doesn't work, we want to have versatility in doing other reactions. So on paper, all of these reactions work, right? We can easily just say or claim that this will go to the aldehyde, but in reality, will that actually work? And so that's why there's so many different oxidations, because we want to have a toolbox, right, of different reactions we can utilize. And so let's look at one more here. This is the, again, another sort of person-named reaction. We're going to start seeing more and more of those, which is called the Des-Martin oxidation. And this chemical here, this molecule here, is the Des-Martin periodinane. And you notice, right, this iodine has a lot going on. There is actually a lone pair here, right? So this is called a hypervalent iodine. And it is the crux of the reaction here. And so we can do, once again, the same thing, take a primary alcohol, convert it to an aldehyde, or secondary alcohol, convert it to a ketone. And so our final product here would be a ketone. And so what is the mechanism for this? A little less complicated. It's kind of weird, which is why we'll kind of take a look at it. But it's still something we can look at regardless. So, okay, for this reaction mechanism, where we have our alcohol again, we have this DMP, right, this big old molecule over here. And we have all these acetyl groups. And I should note here off to the side, when we say acetyl, that refers to this motif. Okay, so we have these sort of esters coming off this iodine, right? And so what happens here now is this this oxygen will attack the iodine, and one of these acetyl groups, right, because they can do resonance, leaves. And so now we have this whole oxygen species here, and I'll abbreviate these phenyl groups. And I'm actually going to abbreviate the rest of this so we don't have to keep drawing the same thing, right? The rest of the molecule is still here. We're just not going to draw it in. And we have, right, this protonated oxygen species. Right, now this oxygen acetyl group is going to come through and grab that hydrogen from our oxygen here. And then in this final step, sorry, and then we have, right, a hydrogen here, and it's like with that last reaction we saw, that pseudo SN2 reaction, we're going to have another equivalent of our base here come through, right, and remove that hydrogen, right, make our double bond to the oxygen, and then we have this last acetyl group on that iodine, that iodinane leave, and we end up with both our right, both our ketone, right, which we've shown up above, but this sort of catalyst here has changed. Now this iodine has 2 lone pairs on it and just 1 acetyl group. Again, it's not a reaction mechanism I'm going to have you know, but here it is. Okay, there's sort of that process taking place. So we'll go ahead and cover some more of these reactions in class, right? Look at some more problems with them, and then we can go over either these mechanisms or any questions you guys might have in terms of clarifying some of these concepts a little bit. So in general, right, just a lot of different ways we can go from primary and secondary alcohols to ketones, aldehydes, or carboxylic acids.